computer. Okay, so hello everyone. As always, thanks for joining us another day. So today is day 6 of the DeSIRE inversion code tutorial. And today we are going to continue learning how to perform non-LT inversions with DeSIRE. And what we are going to do today is to learn a bit more some options that we have for improving the results of the inversion. So we are going to start from the profiles that we synthesize in day 5 run 1 and using the configuration from day 5 run 2, and we are going to improve it. Okay, so we are going to focus mainly on 2 options, although I will explain some additional ones, but in detail we are going to cover just 2. And these are wavelength dependent weights that I will explain later, and also how using different initial atmospheres with different certifications and values for the atmospheric parameters can help also improving the inversion results. Okay, so before that, if you remember, we had 2 questions last week. They were related to the threshold. So for example, Dato, he asked that if he understood correctly that 0.1 threshold was equivalent to a 10% change, absolute change in temperature, then for example, a big number like 9, does it mean 900%? And then the answer is yes. And the idea is that if you want to reproduce something like LTE inversions, you just put a large number, 9, 10, maybe 11, and then the code will basically work as a SER. It will work almost an LTE. And if you want to have non-LTE and play with the speeds, then maybe 0.1, maybe 0.2 could be reasonable value. And if you want to force non-LTE, then just put 0. And then in every iteration, we recompute. So we call RH, we solve the non-LTE problem, we recompute the atomic populations, we also compute the profile, and we have the new departure coefficients, and then we repeat the process. But as we said before, in general, if there are no big changes, mainly in temperature, there's probably no need for that. So we assume between 5 and 10% changes is reasonable to keep the departure coefficients from the previous cycle. Okay, and then also Ryan Campbell, he asked, is it possible to have a different threshold between cycles, just in case I want to speed up things at the beginning and then maybe have a final run where I force the code, or maybe 2 final cycles where I force the code to have to always recompute the departure coefficients, and then the answer is also yes. So I think this is nice. I was not sure, so it's good that Basilio had time this week for discussing it. And if you have an additional question, just let me know. And if not, then just as always, thanks for the questions. And then just move back to the programs. Okay, so then yes, let me minimize this. So then today we are going to have 2 folders. In each folder, I will always have, as always, a script, an ideal script where I have a lot of information, and then some things for running the code and explain you how it works. So then let's start with the day 6 run 1. There's a lot of things there, but just let's focus on the script. So then the idea is when you want to improve the inversions or the results, you have the option of changing a lot of things, but I think there are a few ones that they have a big impact on how the inversion could be. It could be much better or much worse. So then the first one is, of course, the number of nodes. So just as a reference, just let me move a bit down this because Zoom is in the middle. So then just remember that you can play with nodes here, and depending on the values, you will have a constant value, a linear gradient, a parabola, or just complex fluctuations. Okay, so then there, I think, just mention that be aware of the number of optical depth points that you have in your atmosphere, because this will just define which set of nodes you can use. Also, don't forget that you can use also the automatic selection of nodes. So just as a general thing is that here, if you put 1, then the code will evaluate based on response functions if the maximum number of nodes that you are given in a cycle needs to be used, or maybe with fewer nodes, the code will still get a good solution. So in other words, so for example, if you have here 1 in this sentence, and in the last cycle, the code can decide if it uses 5, or maybe if it sees that using 5 doesn't improve from 3, so then it will just use 3. It's important just to realize that it will never use more nodes than the ones you have here, okay? Unless you put an asterisk, okay? But just don't use asterisk for now. The important thing is that this will be the upper limit for the automatic selection of nodes, okay? So then just let's go back. And then this is an advice, and is when choosing the number of nodes, you have to also balance the number of free parameters to use. So in the free parameters, you can see them as the number of wavelength points times the number of Stokes parameters that you have information. So usually when you have the 4 Stokes parameters, and imagine that you have, I don't know, 100 wavelength points, this is already 400 wavelength points for free parameters. So then this means that you can play with this configuration of, for example, nodes. So it's 5, 1, 3, 3. So imagine having 20, 25 nodes. If you have 400 free parameters, it's reasonable to have this number. But on the other hand, if you have, for example, an imaging instrument and you're observing one line and you have like 6 points, so then you're already having around 20 or maybe 24 free parameters. So then playing with a lot of nodes here is not advisable. So having the same number of nodes as free parameters is usually not the best option. So try to always be with less number of nodes than the total number of free parameters you have. Okay. So then this is what basically I said here. Then changing the number of cycles. This is just simply that sometimes you can have this configuration here, and then you said, okay, maybe I will just add here a third node on inclination and add an additional cycle, basically keeping everything almost the same, but just adding one node in one of the parameters, and this can help also. So you don't need to change all the parameters in every cycle. Sometimes you can have one cycle, one extra cycle, where you just change one or the other, that it seems that it's not getting good results, for example, in linear polarization or something like that. So just play with the number of cycles, and you don't need to increase a lot the number of nodes for all the atmospheric parameters in each cycle. Okay, so then just let me go back like this. Okay. And then, yes, and then here is where things could be maybe a bit more complicated. So just let me go slow. So you have the option of weighting. So here you have weight for Stokes I, Q, U, and V. And weight here means that when the code is evaluating the chi-square value to decide which parameter needs to, which atmospheric parameter needs to change and at which height, it evaluates the chi-square value. That is the difference between the profiles. But there, in that evaluation, there are a lot of factors included. So the weight is one of the factors that you can put to enhance or penalize certain things. So then in this case, what we are saying is that we know that Stokes I is important, but as we are interested in the magnetic field, we want to have more weight, because the errors that you can have when not fitting perfectly Stokes Q, U, and V compared to Stokes I are going to be always smaller, because they are a percentage of the total intensity that you have. So then we want to say the code that even if we are not fitting as good Stokes I, we want to have a better fit for Stokes Q, U, and V, because this is the only way of getting information of the magnetic field. Not the only way, but it's one of the best ways of getting information of the magnetic field, because also Stokes I can give information. So then it's essentially that you have an equation that is adding terms, and you want that one of the terms weights more for the final computation, because that term you are more interested on it. And in this case, it's Stokes Q, U, and V, for example. Okay. So then this is just between Stokes, because they are different, because Stokes I and Stokes V, they are going to be always with different amplitude. And this was always available in DeSIRe. But now for DeSIRe, we have added an additional one that is based in the same pattern that we saw before, but now is wavelength dependent weights. So what we are saying is that if you understood that even if Stokes I is always higher, we want to give more weight to Stokes V, for example, because we want to fit it better. So now we have the same discrepancy between the amplitudes that you can have for photospheric lines and chromospheric lines. So then in this case, the motivation was that the code needs to know somehow that we are interested in fitting very well chromospheric lines, even if that could be that the error in the photospheric lines is a bit larger, because the amplitude of the chromospheric lines is going to be very small compared to the amplitude of, for example, nylon line sensitive to the magnetic field. So then we want to also have an option of enhancing or penalizing the importance of a given spectral region in the computation of the chi-square value. And this is what we are going to check in detail in this first procedure. But the concept is that the code doesn't know how the chi-square behaves, and you have the option of telling different things through the weights to just enhance or just telling the code to go one route instead of another. Okay. If there's any question, just let me know. If not, I will try to continue, but going slow. Okay. And then another option, a fifth option that I think is important also for getting better fits, is that you can start inversion with one gas atmosphere, or you can start inversion with different gas atmospheres. And the idea is that the code is going to map a value of chi-square values, but depending on where you start with an atmosphere, the code will start in a, let's say, a given position of that value of chi-square values. But sometimes there's some kind of local minima there. And if you start with an atmosphere that is very close to the local minima, the code is probably not going to be able to move from there. So if you have different initial atmospheres that will move the initial position of the code, the chi-square map, in different locations, then you are favoring to let the code to explore different options that will produce a different chi-square value that sometimes could be better than just using one atmosphere. I will show you later how we can do that. It's implemented automatically in the parallel version, but today we are going to learn how to write a code to do this and understand why it's different and understand a bit more about the process. Okay, but essentially these are the points I think you can experiment a bit at the beginning when you have a map and you want to start preparing the configuration. You should work on that. And today we are going to focus on number 4 and number 5. Okay, so then before starting with number 4, is there any question? No? Okay. So then the first thing we need to do, sorry, is to create a wavelength dependent weights file. Okay, this is relatively easy. What we are going to do is to create a file with the same format of the profile file, the input profile file, but containing different information. Okay, so then let's start reading the input profile that we are going to embed, and just to get information of the index and the wavelength and everything. And then we are going to create a Stokes I weight, Stokes Q, U, and V weights that are just the Stokes I, the Stokes profile that we have just loaded from here and multiplied by 0. And we are going to add 1 just at the beginning to have all the weights with the same value. And the important thing here is that 1 in this case, so I mean, the weights are a multiplicative process. So 1 is multiplying the weights that you are having here. Okay, so then if you already have a ratio of weights between the Stokes parameters, like 2, 3, 3, and 5, you don't need to put here 2, 3, 3, and 5. because if you do that, you are multiplying these two times the other two. So what we are going to do here is to create differences between wavelengths. But the difference and between the Stokes profiles, I recommend you to give it just here, because you don't usually want to have a different ratio between Stokes profiles for chromospheric lines and photospheric lines. Usually you want to have the same ratio, but then you can add another ratio between photospheric and chromospheric lines. Okay, so then essentially, if you do a change here, try to do the same change for the Stokes, for the 4 Stokes parameters, and then the differences for the weights for the Stokes parameters, just add it here. If I'm just confusing you, just let me know. If not, I will try to explain it a bit better later. So then essentially everything is 1. So for now, if we create a weight file like this one, then we will have the same result as the last tutorial, okay? Because we are not adding anything different here. So then let's try to add a different weight, but just for the regions of the calcium 8498 and 8542 line cores. So I just by eye decided that probably the line core region of 8498 is 250 milliangstrom, and the one for 8542 it's around 350, but it's just by eye. And in fact, I recommend you as a homework to try to determine how much kilometers this wavelength shift means, so then to understand more or less if this is reasonable or not. Okay, so then I look for the index where I had this value. So just let me run here. And then what I'm saying is that let me show, just let me check what is the index and wavelength for those indexes. And you see that 538 is index 3, that is the calcium 8498 line, and the wavelength is minus 260. And then I just check that the other wavelengths, sorry, the other indexes correspond to positive 260. Okay, so then what we're going to do the same for the calcium line. If I do this, we have that now for index 4, this value corresponds to minus 360, and this one 360. Just as a note, we are using 20 milliamps on steps, so there's no 250 or 350, but this is just because we set the spectral step like this. So I just put it 260, but you can decide this later. Okay, so then now we have an indexes, so the spectral range for the calcium 8498 and 8542. And now what we are going to do is that between those values, this spectral range, we are going to give a different value. And as I said before, it's the same for all the Stokes parameters, because we don't want to mix things between the control file and this one. And the idea is that I will show you today what happens when you have 1, that is the same as before, then 10, 100, and 1000 more times. So the weight is larger, 1000 times larger for the calcium lines, okay? So then when we have this, we just write with the same sentence that we write the profiles, but with the extension WHT from weight. And we just save this vector that, if you remember, it was 1 for the whole spectrum, but then we added 10 just for these 2 spectral regions, okay? And then we write the profiles. So just as a reference, this is how the profiles look. So you have index 1, then if I move fast, index 3, and then this is Stokes I, Q, U, and V. And then the weight that we created is like this. So you have index 1, and then everything is 1. But if we go to index 3, that is this one, and we go to minus 260, sorry, because I'm going a bit fast, here. So you see that now it's 10, 10, 10, and it's the line core. And then after 260, it becomes 1 again. Okay, so then this is the weight file that we create. And then with that, we can just run the inversion. Just as a note, if you run the code without any WHT file, the code will say, I'm looking for input 1, WHT. Well, it will look for the profile name that you have here. Sorry, I forgot about that. So if this is your name, so the input profile has this name, so it will look for input-1.wht. So if it doesn't found any file, it will tell you a message. We didn't found the wavelength dependent weight file. But if you have it there, then the code will run without saying anything, indicating that it's using it. So just as a double check, run first the code without any WHT file, and you will see the message, and then create the file and run again, and you will see that the message doesn't appear anymore. Okay, so then with that, we have already our wavelength dependent file, so we can just run the code. And this is essentially the same of last week. So I will just go to the results, but just let me quickly just explain what we have here. So we run the code, so we get the results. We are going to compare the input profile. So we read it, we divide it in the 3 spectral windows, so 630, 8498, and 8542. And then we have the vector. So now we read the result from the inversion. Remember that it was the name of the input atmosphere. We started with guess.mod. And then is dash the cycle. The last one is 3. And then dot pair. Okay, so this is our output profile from the inversion. And then we do the same. So we break the profile in 3, and because we are using 3 windows, 630, 8542, and 8498. And now we are going to plot the results. We are going to compare the input iron profile versus the output from the DeSIRe code. We're going to do the same for calcium, and 8542 and 8498. Okay, and then we are going to compare the atmosphere. So just let me just cover also this, and then we will just compare plots. And for the atmosphere, it's the same. So we read the input atmosphere. In this case, as we did the synthesis, we have it, but in general, with observations, we will not have this step. Then we have the initial atmosphere. So I want to also show you how the code moves from a given initial atmosphere, how it can move to getting as close as possible to the target. And this is the result from the inversion. And we're going to do the same. We're going to plot in black the initial atmosphere, in red the fitted atmosphere, and then with the dot line the initial atmosphere that we started the inversion from. Okay, so then let's go. This is already the Dropbox folder, so I have always the figures here. So let's start. This is what we had last. Sorry, this is the atmosphere. This is what we had last week. So this is weight 1. Okay. So now let's start with extreme case. So imagine that we are providing a weight that is 1,000 times larger. Okay. So then if you have this, we can say that the code is following our instruction because it's fitting the core as much as possible, but we are giving so much weight that is forgetting about anything else. So then the fits in the wings and also in the iron lines is not good. But what I wanted to show you here is that this is the impact that you will produce in the code. So if you give weight for a given wavelength region, then the code will try to better fit that wavelength region. But if you give too much, then the code will not be able to. So the errors in the other parts will have no impact because it's so important to have a tiny part of the fits well done that is not taking care about the other things. So then I put it different examples, but I think as the time is limited and you can check it later on, let's focus on weight 10. Okay, so then if you go to weight 10, so here things are reasonable and in fact are much better. So just let me go back to here, and this is weight 1. So it's difficult to show it to you here, but just you can check that this, for me, it looks better than this one, that the red color is a bit down. So you can check it at home. So then we are starting to see that it's getting better, and the same for Stokes V. So if you compare this one that is in fact doing this shape very well compared to this one, that the amplitude was larger, it was going down here. So we are already getting what we wanted to have. That is that the fits of the calcium lines are getting better. Now let's compare the same for 8498. So we do this. So then you can see, or I hope, that here the curve was a bit down and here is a bit up, but still it's closer to the line. And the important thing is Stokes speed. So here this is weight 1, and you can see that it's trying to match this, but you can see the black and red colors, let's say this way. And here you basically see red on top of black. So then just changing the weight and telling the code that it should try to fit better this region, even if it means not so good fits of the photospheric lines, we are seeing an improvement. And then the key is that what happens with the photospheric lines. So you can check the other weights, but let's focus on the 10 and 1. So this is what we had last week. Let me move this. If it doesn't, okay, now it moves. So you can see that it's a bit, so this one is the new one. It's a bit worse, but still it looks good. And also this one again is a bit worse, but still looks good. So then it means that, of course, we are losing a bit in the photospheric lines, but I think we are gaining a lot in the chromospheric lines. So then let's check if we see something in the atmosphere that is different. So let's open the atmosphere here, and then this one. So this is weight 1 from last week, and this is the weights 10. So just changing the weights, we have not changed anything else. So then temperature, I would say that it looks similar. In this case, it was a bit above, and in this case is a bit below, but it's very close in both cases. But here I would say that magnetic field is much better. So here it was just a straight line, but it was good it was getting reasonable fit, so it was okay. But here we are much closer to the black line. Although still microturbulence here was before, here it was not so good, but yeah. And then velocity in both cases, it's better here because this one goes farther before in optical depth, but still it's not so good. So I think we should try to improve it a bit. But the important thing is that just telling the code, I want to have a bit more accuracy in the core of the chromospheric line, so try to fit it a bit better. We are improving the atmospheric result. So I think this is good, and this is the first step towards having a configuration that is really, really good. Okay, so I think this is basically everything that I wanted to say here.
So Carlos, can
yes.
we also put like there is a different part which you just said that the code itself knows that the chromospheric line has to be fitted better than a photospheric line because the signal in chromospheric lines is less. Yep. So is there a way, if similar to giving this extra weights to core of the chromospheric lines, can we similarly give at least to the cores of photospheric lines so that this discrepancy, like the photospheric line is not fitted well now in this case, when you give more weights to chromospheric core. So
yeah, I think,
yeah, it's a complicated overlapping thing.
Yeah. Yes, no, I think it depends. So I would not give weight for the core of the photospheric lines because they are so narrow that basically you can have, so it would mean just changing 1 or 2 points. So I will just give weight to the complete photospheric lines if you have a lot of continuum, for example. So imagine that you have spectrograph and you have, or for example, in the calcium window. So imagine that, let's say here. So maybe instead of having the same weight in all this spectrum and all this spectrum, maybe you can give a bit more here because we have 3 lines there, and maybe also here. So I would do that depending on how much continuum points you have. But I think for the line itself, so maybe let's say that you are giving a few more weight in this region instead of the winds, I think probably for the photospheric lines, you will not see too much change.
Okay.
But in terms of photospheric lines and continuum, then maybe it's helpful. So for example, here, I'm not sure if maybe giving a bit more weight in this region could help, because the truth is that it's all working already very well. So I'm not sure if you will see differences,
Yeah.
but if
I
you
mean,
are,
like
yeah,
for iron lines, which you showed, like
yes,
now because of calcium line, you have given more
sure,
weights. So
yes,
the fit in iron lines is not
yes,
that good as it was used to be
yes,
without any weights.
yes, yes. So let me say something. So let me show you the the next
Yeah. Okay.
configuration option,
Okay.
and
Fine.
you will
Fine.
tell me
Okay.
if your question remains. Okay,
Okay. Yeah. Sure.
because
Okay.
we are going to improve it. So, but I understand your question. So let's discuss it again
Mm.
at the end. But let me show you first what happens when you have different initial atmospheres. Okay.
Yeah. Okay.
Okay. Thank you.
Yeah.
Okay. So any additional questions? No? Okay, so then just as a comment, and I'm always trying to explain what I write here, but you should always, or at least try to read everything that I wrote. So for me, the important thing is that I don't have a fixed value that I can tell you for weighting more chromospheric lines versus LTE lines or photospheric lines. I would say that between 2 and 10 is reasonable. So I mean, the calcium lines, for example, weighting between 2 and 10 times more, but there's no real value because this really depends a lot in the configuration and in observation. So I would say that my recommendation is when preparing the map, try to embed with maybe 2, maybe 5 and 10 times larger values on chromospheric lines, and embed maybe like 10 or 20 pixels and get an idea if you see a tendency. So for example, with 5, you get better results and everything looks okay, or maybe with 2, or maybe with 10. More than that, I think no. So I mean, maybe 100 or 1000, I think is not good. But between 2 and 10, I cannot really say. So in fact, I cannot tell you if getting 5 in this example will improve the result because I didn't check it. But I think it's reasonable between 5 and 10. So you should also explore that because I don't have value that I can prove it's from some background study that you can use. But I think between 2 and 10 you can try. Okay, so then let's go to the initial atmospheres, and then we will check again with Nancy's question, and we will discuss it a bit more. Okay. So then we are in a different folder. So it's just, I will give you the compressed files containing this. And then again, it's another file, another script, ideal script. In this case, what we are going to do is to take the previous one. So the configuration from the last week, adding weights 10 times more larger for chromospheric lines, wavelength dependent weights. And then we are going to check if we can improve this a bit more. Okay, so then what we're going to do is to initialize with 5 different atmospheres. As I said, the idea is that you have, let's say, a map of chi-square values, and then depending on your initial atmosphere, the code will start in one point on this map. And then if you change the initial atmosphere, you can move the code completely on that map, and then it can get to a, let's say, better chi-square minimum. So then as more atmospheres you have and the more different they are, you have more options of cover much more options for getting a better chi-square value. So in this case, for simplicity, I'm going to keep the same temperature. So we are going to just use FAL, but my recommendation, and I will prepare the files for you, is to have also different temperature electron pressure relation. So you can have a FAL model, HSRA model, maybe this sunspot deep and hot and cool Umbra models. So having a lot of combinations of temperature electron pressure relation, and also then microturbulence, velocity, magnetic field, and yeah, magnetic field vector. And those I recommend you to have it flat. So the magnetic field, a constant isotopification with height, and then the original temperature electron pressure relation from the model, the FAL or the sunspot model. Okay, so then in this case, as we are going to have flat stratifications and the same temperature, I'm going just to create vectors that contain scalars that are going to be the amplitude of the atmospheric parameter. So then, for example, this velocity is going to have, so we are going to create atmospheres that will have a constant certification that will be -2 kilometers, 1 kilometer, 6 kilometers, 1 kilometer, -5 kilometers. The same with magnetic field, 100, 500, 1,500, 550. Okay, so we just create a vector with different scalars, and we are going to run a loop now. Okay, so just follow me, and then if you have any question, just let me know. So the idea is that we just defined the number of atmospheres with this variable, and then we are going to create arrays where we are going to save the profiles we get from the inversion and the atmospheres we get from the inversion, because we want to store all the solutions and then at the end compare them, and also to pick the best one based on the chi-square value. Okay, so then we read the profiles just to know how many wavelength points we have, if we have enough stored somehow. And this will be the wavelength dimension that we have here. So then we are going to create an array of Stokes I profiles with a dimension that is wavelength points times the number of initial atmospheres that we want to try. Okay, so in this case it's 5. And we are going to do the same with the atmosphere. So we have that we read the initial atmosphere that we are going to use, and then from there we get the number of optical depth points, and then we can create, for example, a temperature array that is number of optical depth points times the number of initial atmospheres. So we want to run 5 different atmospheres, so we want to have 5 temperature solutions, because each one would provide a different one. And then we want to also have an option to know which inversion was better. And for that, we read the chi-square value that the codes provide. Okay, and in this case will be just the number of atmospheres. And also, sorry, the same for microturbulence, filling factor, and stray light. These are only scalars, so we don't need a vector times the number of initial atmospheres, so just the number of initial atmospheres. Okay, so then we are going to run a loop, and in each iteration of the loop, we read the original atmosphere, and we created a new one based on the atmospheres that we had before. So for example, magnetic field is the same one we have here times 0. So just to make it flat, just to be sure that it's flat, plus one of the values that we defined it above. So it could be 1,500, it will be 50, or it could be 500. Okay, so then we will have that this guess mode will be different as we run the loop. It will have the same temperature, because as I said, for simplicity, we are not changing that. But we are going to have different microturbulence, field strength, velocity, inclination, azimuth, and all of them constant with height. Okay, so then we define the atmosphere, we run the code with the same configuration as before, including the weights that weigh 10 times more the chromospheric line. Okay, then we read the output profile and we save it in our Stokes I array that, sorry, I'm still not recovered. Our Stokes I array that we defined above, that was wavelength times number of initial atmospheres. And the same with the atmosphere. So we have that we read the output from the third iteration, and then the temperature array will be the number of optical depth points, and then a fixed initial atmosphere, and it will be equal to the solution that we have in this iteration of the loop. Okay, so then just as a note, we don't have the errors yet. We are working on that. So in principle, if you want to have also the errors for the different solutions, you would need to have another set of arrays like this one, and you will need to read something like guess-3 dot error. And then you can have also a set of arrays, because the errors will be with the same dimension of the atmosphere. Okay, and just as a comment, because I was really having fun when I was preparing this. So I did this loop, this inversion, this trial a lot. And when I say a lot, it's really, really, really a lot. with Basilio, that is also here, with in my PhD almost 8 years ago for Hino the data and SER. And the concept is the same. So you want to have a configuration that maybe you like, but you also want to have different initial atmospheres, and then you want to run it for those initial atmospheres and then pick the best one and also compare different solutions. So this I did in my PhD, and although it doesn't look as well, it's really nice. So I hope you can enjoy reading at least the program and seeing how it was done 8 years ago. Okay, and then we need to read the chi-square value because we want to have an option to tell, okay, which atmosphere provided the best result, and then try to understand that. So then we just open the inversion.chi value, file, and then it has 3 values. Just as a brief explanation, I put here a sentence, but I will dedicate part of a class in the future to explain them exactly, and also to tell you how to compute them in case you want to really understand how the code does it. So then in the case of C1 is 1 divided the square root of the chi-square, DeSIRe chi-square, that is C2. And this one, as I say here, is really, really complex. I need to sit down. I think next week I will sit with Basilio to write down all the equations and prepare an ideal script. He's smiling because I think it will take time.
It only includes the weights and some
notes and
complicated.
Yes. even Basilio has to check the notes to write the formula down. Okay, but the important thing is that C2, even if it's complex and everything, it's the one that DeSIRe is using internally. So this is the one, the real one, the code is using for this, for deciding which atmospheric parameter needs to change and everything. So this one is the one that we are going to use now. And then C3 is a different combination of that chi-square value times the signal to noise that you have here. So yes, this one. So you can play with this signal to noise based on your data, and you can have a different information based on that. But for now, for today, just let's focus on C2. And the important thing is that we run the loop, we store that C2 value. So just see here the sentence, and then we are going to check it later. Okay. So I'm not going to run it here, but just try it. I think it's like 2 minutes or 3 minutes. So it's relatively fast. And then the important thing is that when the loops end, because I wanted to show you just one plot, I'm going to repeat what we did in the previous example. So we read the input profile, we divide it in different spectral windows so to make the plot. And now we are going to plot, so to overplot that input profile versus the best one from the 5 different atmospheres. So for that, we need to check which one provides the minimum. So if we print chi-square value, we have this. And as you can see, so here is lower is better. So there are 2 results that are much better than the other 3. And interestingly, this one is exactly the same atmosphere that we have been using in the previous test. So maybe by chance, we started with an atmosphere that provided a good solution. But even more interestingly, this one, that it was a random atmosphere that I created, provides a better result. So what I'm going to show you now is why this atmosphere provides a better result, and try to understand that in this case, we can trust the code that if a chi-square value in general is better, probably the fit in general is better, and the atmosphere that we are getting is also in general better. Okay, so just I want to know which index provided the minimum, so I just define this value. So then pos is the index from the 5 different atmospheres that correspond to the minimum. So then I'm saving the Stokes profiles from the arrays, but only for that index. So we are going to make now the same separation of the spectral windows to make the plot. So this is the same, and these are the plots, okay? And this is what I call best. So just is the same, 3 spectral windows, and then the atmosphere. Here is a bit different, but just basically the same. So the input atmosphere, this is the same. Then for the initial atmosphere, that this was the dotted line. So we need to read the initial one because the temperature is always the same, so this will not change. But the microturbulence velocity and field strength will be the array that we define it at the beginning for the index that provided the best result. Okay, so if you are checking this and you have an issue, just send me an email and I will explain you later. Okay, and then the atmosphere that provided the best result is the output temperature arrays for the index that is correspond to the minimum of the chi-square value. Okay, so then the plot will be the original, so the atmosphere that we use for the synthesis, then the atmosphere that obtained the best fit in red, and then in dot the atmosphere, the initial atmosphere that produced the best fit. Okay, so then just let me stop here and let's go to the figures that I think you will be able to understand a bit better. So let's start with 8498 and this one. Okay, so here if you look, for example, Stokes I, it looks like it's a bit worse for the 8498 line, and Stokes B, I would say that also is a bit worse. It's still much better than what we have without weights, but between weights and weights plus initial atmosphere, I would say that maybe a bit worse. Okay, so now let's go to 8542, and then here, so this is this one is with weights and no, so just one atmosphere, and this is the best one. So here again, it looks like it's a bit worse in the core, and also Stokes B, it also seems that it's not so good. So it doesn't seem that the chi-square value it's really saying something that we want to see. But how about the photospheric lines? So let me go here to this one. So this is with weights and just one atmosphere, and this is with 5. So then here things are starting to get much better. So you see this is the linear polarization, and this is the one with the best solution. And if you go here, you have the same. So these one are much better than this one, and this one are a bit better than this one. So we are losing a bit on the calcium lines, but we are getting better results on the photospheric lines. And now the key question, and this can only be done in this test. With observation, we will not be able to do it. So how about the atmosphere? Are getting better or are getting worse? So then this is with weights, and this is with weights and 5 initial atmospheres that I just quickly prepared. So then temperature, it's a bit worse. So this is closer to the black line than this one, and this explains why the chromospheric lines, they are a bit worse. But how about velocity? So this is what we had before, and this is what we have now from the best solution. And I think this is really a much better improvement. Microturbulence is also a bit better. It's not exactly the black one, but it's a bit better. And I would say that also the magnetic field is a bit better than this one that was here was not so close, and then it was just moving up and then moving up. So in general, even if the calcium core profiles look a bit worse, I think this general better chi-square value, it's good and is providing better general results in terms of atmosphere, although maybe temperature we lost a bit, but I think what we are gaining in velocity, it's much better than, or much important than what we are losing here, because maybe this is a few hundred, not a few hundred, probably 100 Kelvin, something like that, and here is just like 2 kilometers. So I think just adding initial atmospheres that are a bit different, we are allowing the code to explore different options that get an overall much better result. Okay, so then let me just go to the discussion. But is there any question before going to the discussion? No? Okay, so then one exercise that I think you can do is to now compare the 5 different atmospheres. So why some atmosphere has a very bad chi-square value. So what is the code doing there? So I think you can plot them because you have it as an output of the loop. And then my recommendation is that For a given observation, for example, imagine a Quaisite map, I will just look for representative profile. So for example, a granule, an intergranule, a network patch, something that almost no magnetic field. And then I will try to embed like 5 different pixels from representative regions with a given configuration of profiles and also with a given configuration of initial atmospheres. And then the idea is that try to combine everything in the sense that you get reasonably good results for all the profiles. Don't try to fit very, very, very well the granule profile and then have a very bad result for the intergranule or the network, because then your map will be a bit biased. So try to play a bit with different initial atmospheres as varied as possible. So strong magnetic field, weak magnetic field, hot, cool, and things like that. And in general, I think the code behaves so well that usually it gets to a good solution, and you can expect that this good solution, as you saw in this example, in general is better than you can have with a different initial atmosphere that provided a different chi-square value. So I think this is very, very good, and I was very happy to see how the code behaved, because DeSIRE behaved like this. DeSIRE is much more complex, so I wanted to see that behave in the same way, but I needed to do a lot of tests, and I think it's really behaving very, very well. And just as a warning before going to the summary, the chi-square value that DeSIRE is computing, as Basilio said, it depends on a lot of factors. It depends on the weights, it depends on the nodes, and everything, and a lot of things. And the problem is that if you want to compare the solution from one configuration to the other, you cannot use the chi-square value that you have now, because they are computed with a different set of conditions, so they are not comparable. But Basilio is already working on just computing a general chi-square value that will be the difference of the Stokes profiles. And this will be as a reference if you want to compare one configuration to another. So imagine that you are saying, I want to know what happens if I put 5 nodes in temperature or 7 or 9. So then we are going to add that an option in the .chi file where you just compare just the Stokes profile. So then if you are changing configurations and you want to see which one is the best one in overall, then you can do it. But for now, you can just compare results from different initial atmospheres, but keeping the same configuration. But my advice is pick 5 different profiles, try to embed them with maybe 5 atmospheres and with the same configuration. And if all the profiles, they are reasonably well fitted, then you are set to go. You are ready to go and just embed the map. Okay. So then, before summary, is there any question? Nancy, how about this? So what I wanted to say is that I understand your question, but I think just weighting the profiles, the photospheric lines with a normal weight, in the same weight, I think it's enough. You may weight them above the continuum if you have a lot of continuum, but I think the code should be able to do this. So it should be able to try to fit the best all the range and be able to fit the photospheric lines very well, even if we have a bit more weight in the chromospheric lines.
Yeah, okay.
Okay. Yeah, Dato, yeah, you have a question? Yes.
Yes, Carlos.
Yeah.
So when you are selecting these 5 different initial models,
yes.
So what do you think? What should be the strategy? Should we select like more or less a random distribution to cover the range, different parameters, or it's better to estimate somehow, to guess somehow the velocities or magnetic field, for example, from Doppler shift, or I don't know, whatever.
Yes.
Okay, so you will use and then select atmospheres close to that preliminary estimated values.
Yes, that's a very good question. So in general, I'm going to prepare a set of atmospheres for the course, maybe between 10 and 15. And there I will try to cover a wide spectrum. So cool atmosphere, hot atmosphere, positive velocities, negative velocities, weak field, strong field. And that should be good for any map. But if you, for example, compute Doppler shift very fast of all the profiles that you have, and then you use that velocity for initializing the inversion, it could be better. And in fact, the extreme is what Ricardo is working on, that is using neural network, you can estimate a bit the atmosphere that you could expect from the observed profiles, and then use that as an initial model. So I think it depends on how much time you have to dedicate to the map. And in fact, you can have even another option that I'm thinking now is that you can start with the set of atmospheres that I will create. And then depending on the results, you can also try to initialize again with an atmospheres that you got and try to just 1 or 2 cycles and try to check if things get better. But my advice, because I always try to keep things as simple as possible, is just start with a set of wide atmospheres, like 10. And if you see that the results are smooth, you see that there's no salt and pepper or not a lot, I would say that this is probably good enough for most of the scenarios. But if you're starting to see that velocities are always Doppler shifted and maybe red shifted when it should be like blue shifted or something is going on, then you may need to tweak a bit things. But for me, I think DeSIRe is really robust, like DeSIRe. So just allowing the code to start from different points, I think it will always give you a good solution. And the truth is that we will check this in one of the following classes, because we are going to use the Bifröth atmosphere that is really complex, it's very sharp. So 1 pixel could be blue shifted, 1 pixel could be red shifted. And we are going to start with a set of atmospheres and let the code move from there. And you will see that the code will give you a smoothness that is between pixels, and the code doesn't know about this smoothness because the code only inverts 1 pixel at a time, and it doesn't know about lateral or any correlation. But it's robust enough to give you a smooth result. So I think all the options are good, and I think we should explore them. So if you want, I recommend you. And in fact, I think Ricardo is onto something, because he's training a lot the neural network to just have a map, and then from there try to obtain an atmosphere. And if it's reasonable, then it means that you can speed up your inversion, because you don't need to do, imagine, 5 cycles. You maybe just need to do 2. But I'm always a bit conservative in the sense that if you give a constant magnetic field, then the code with 1 node can move it in all the ways it can. But if you give already an certification for magnetic field, then with 1 node it's not enough. So you need to start from 2 or 3. So I think here is just like a different approach, but both options, or all the options that I mentioned, I think they are worth trying.
Yeah,
okay.
I see. Yeah.
Okay.
Yeah. So mostly we need to do the experiments, and code this sort of indicates which direction we should do the refinements, right?
Yes. But the idea is that I will prepare like 10 atmospheres, and my recommendation is to start from there. And if it looks as smooth that I hope it will be, then I think it's probably okay. So I think, Basilio, you want to say something?
No, I was saying that I don't know if you have explained that when you use several initialization, the code is running in order, that if you reach a chi-square threshold, then the code doesn't try with other initialization. Just if you have reached, I don't know, you can select, you can set my threshold in chi-square is this. And then if just with the first initialization you have reached that, then the code continues with the following pixel. Then you can put, I don't know, 10 initial model, but nearly never you are using the 10 because you are reaching the chi-square threshold at 3 or 4, something like that.
But that is the chi-square that you were showing today now.
Yes.
So if you use it, have different configurations, that might be different to estimate what chi-square threshold you
Yes, yes,
Yes.
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 I don't know. This is the Ricardo is using this chi-square
Yes.
for the threshold.
Well,
Is that?
I don't know.
I don't know,
But
because
it's yeah.
I mean, for the threshold, I use the one that the wrapper computes.
Okay.
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 But
For
you,
the, sorry, Carol, but for the choosing the best one, when you run everything, I use the one that you basically produce.
Okay.
but it's fine because we are just changing atmospheres in each scenario. So it's only that at the end, if you want to compare one big run with another big run, then you don't have, as today, the option unless you compute the chi-square by yourself. But between each run, it's just changing the atmosphere and then picking the best solution.
Yeah, sure. That's good. That's fine. But
Yeah.
no, what I was making the point is that based on some experience, you would choose the threshold, say, well, this is good enough.
Yes.
But that experience may come from a different setup, and so you have to be you have to be careful in that.
Yes, that's true. Yeah, I think we can, when Basilio implements this new chi-square that is complete and it doesn't depend of the updates relating with Python routines. We can, this one is the one that we may use as a threshold because it will be the nominal one, and then you can see depending on a given signal to noise how it moves. But just one thing, going back to that. So for example, Han recommended me once to take, for example, the Bifrost synthetic profiles and compute the Doppler shift of the calcium lines for all the pixels and try to initialize with the velocity that we get from that. I never did it because I was busy, but I think it's something that is worth trying because computing Doppler shift is really, really fast. It doesn't take any time. So then maybe we can combine different magnetic fields, something like that, but then maybe you can have one atmosphere that is the Doppler shift that you get, the line called Doppler shift that you get, for example, from chromophoric lines. I can't tell how much different it is, so we should explore it, but there are ways of getting some information really fast. Or for example, weak field approximation, you can also run it and say the magnetic field, let's start with the result from the weak field approximation. This is good. You create a map and you can give it to the parallel wrap and said, I want to start I don't know, 100 times 100 pixels with these 100 times 100 atmospheres that I created from any method. So the wrap accept three options, right, Ricardo? So just a set of atmospheres, the neural network, and this cube of atmospheres that you can create.
Yes, you can compute, you can choose the way you prefer to compute it previously and just feed it as an input. Actually, I was talking the other day with David. I should talk with Luis because Luis wrote this super fast Milne-Mannington inversion code using GPUs and stuff. So it seems that it is super optimized for EST. So probably can also be an option. So you just run a Milne-Mannington inversion that is probably take a few seconds to run and then feed it as
the input.
Input atmosphere. But I don't know the details of the code.
Me neither. But yes, so in principle, that I will just provide a set of atmospheres. I will show you how to do it. And then as time goes, we can evolve or maybe try different options. But at least this hard trial and error of just a set of atmosphere with different configuration, it's going to provide very good and smooth results in terms of 2D. So you will have, if you have a sunspot, it will be able to reproduce penumbra, umbra, and then the quiet sun outside. Okay. So then I think just a summary, I think we have already covered this. If not, please check it at home. And then just let me go back because I'm already late today. So then as a homework, as always, just try to understand the script and try to reproduce it. I think it's important to see the difference of what we did with the weights and then what we did with the different initial atmospheres. I think you can experiment, for example, with weights. You can make it shorter or larger to just check. For example, Nancy, you can also try to, let me see what happens if I just increase the weight of the photospheric lines. I think it's good to try and check how the code behaves, maybe with this pixel or maybe try a few pixels. But I think the best thing is to know or to get used to the code, to know it better. So try things, and if it improves, then good. If it doesn't improve, then you said, okay, maybe this is not the best thing. But I think it's good to try, because I cannot really tell you what is the best configuration. Okay, so, and then again, it's important to realize what means different atmospheres in this some kind of map that I'm trying to draw in the air over chi-square, but it's important that, so just imagine that the code has one way of one path from it can start if you just have one atmosphere, but if you have different atmospheres, it can start from different position of this road, and in the left side, in the right side, or in different locations. And this sometimes can allow the code to get to the best solution, let's say to a different shop. So I think it's just that. So we are giving the code the option to play with things that cannot change in one inversion. So we are helping externally the code to get a better solution. And this is not DeSIRe, this is chi-square based codes. Okay. So then next class, we will start with the Python wrap. So we are going to see how to create the atmosphere for running and then run a synthesis, hopefully. The idea is that we will start with the steps we followed in the paper. So we are going to take a piece of the Bifrost atmosphere. We're going to do synthesis of this spectral region. And then we are going to invert it with maybe 5 initial atmospheres and a given configuration, something normal, not very complicated, and then check how the results are, and importantly, how the smoothness of the distribution. So if the code is able to have different gradients like the atmosphere have in short scales, or if you have a lot of salt and pepper. Okay. So then next week is Easter, so I hope everyone should have some holidays, at least from Thursday and Friday. So then I want to have it 2 weeks, 2 regular weeks after this one. So then next week doesn't count. So then we will meet in April 29th. So before wishing you a nice weekend and Easter holidays, is there any last question? No? Okay, so then enjoy the holidays, relax, rest a bit. Don't eat too much, it's not always and then see you in 3 weeks. Okay, so just let me stop sharing.
Bye-bye.
Thanks,
Bye.
everyone.
Bye-bye.
See you.
Easter.
Bye.
Happy Easter.
Bye.